Okay, so let's get started. Uh, so, so, so basically, this is a webinar on neural networks. I'm going to cover like basics of how a neural network works. What are the components of neural networks? Very basics, and how to train a neural network. What are the processes involved in training a neural network? And what are some best practices to avoid to prevent overfitting and problems like vanishing gradient and all those. So so let's get started. So what is a neural network? Why does it look like this? What is it composed of? So so let's say there is a classification problem. You have a set of data points, and you want to classify them, whether they are in the red area or the blue area. And each of these data points has two variables, x1, x2, and you want to use this to classify them. So so what you can do is take a linear combination of x1 and x2, using the weights w1, w2, and the bias b. So what this linear combination represents is uh, this boundary, this separation line between these two regions, red and blue. And so the output of this equation might not be a number between 0 and 1. It can be any number, any real number. So if you want to get a probability, uh, a number between 0 and 1, you use a sigmoid function. Now, sigmoid function, you can see it looks like this: 1 over 1 plus e to exponential of minus of z. So sigmoid function converts a number into a number between 0 and 1. And so that becomes a probability that this data point x uh, is lies in the blue region. So in this case, the y hat, the sigmoid of z, is 0.8. So that says that with 80% probability, x lies in the blue region. But there might be other ways to separate, to divide these two regions, red and blue. So let's see. Let's see this equation. Now, the difference between this equation and this is the weights, w1, w2, and b. Because given x1 and x2, there can be many linear combinations of x1 and x2 using the weights and the bias. So suppose, let's say, this is the second linear combination using x1 and x2. But again, so if we compare these two, in this linear combination, it leaves out some of these red points out of the red region. These are supposed to be in classified to be in red zone, whereas over here there are many red points in the blue zone as well. So is it possible to get a combination of these two, dividing these two decision boundaries, and come up with a curve, a decision boundary that looks like a curve? So for that, we combine these two uh, linear combinations. So it is just a linear combinations of the data points, the input data points. And in this case, we are just considering this point. So suppose the next linear combination is w1 times 0.7 plus w2 times 0.8, and it gives out a number 1.5. So this is your z, and to convert it to a probability, to a number between 0 and 1, you use a sigmoid function, and this gives a probability that this point lies in this blue region. And you can also see that the decision boundary is now more complicated. It's not a straight line. So neural network is just a linear set of linear combinations of linear combination of the inputs, and we use some activation functions on these linear combination to generate probabilities. So this is more conventional way of showing a neural network. So we use the same 2 points from the previous slides, and we have these two linear combinations, 5x1 minus 2x2 minus 8, 7x1 minus 3x2 plus 1. And then, so these two will give two linear decision boundaries. And then we combine these two with another sets of weights, using another sets of weights, and they give you a more complicated decision boundary. And when we combine them, it will look like this. Again, same. So we have two uh, two input points. So this is for just one example, x1 and x2, and two combinations. And this time, instead of just creating one combination of these two, we have created three. So it depends on what kind of task you have. This could be for a multi-class classification task. It depends on your task. So again, you make a linear combination of x1 and x2, another combination, and then make three different linear combination of each of these two nodes. And if you have multiple layers, so first layer linear, second layer curve, and if you have more layers, it gives even more complicated decision boundary, as you can see here. If you have three-dimensional data, this is a representation of if you have examples with three variables, their first linear combination will be a plane, and a plane in the 3D space, and then this is a more complicated linear combination. So in reality, as we saw in previous slides, we only use two variables for a one data point. In reality, there might be three or even more than three, and there are more than three data points that go as input into a neural network, and we can't represent them graphically, but we make a linear combination of all those points. So for example, one data point here has n variables, so each of this node makes a linear combination of these n inputs of one data point by having different values of weights. So in this case, it will be w1x1 plus w2x2 and plus wnxn. So that's your linear combination. And then you apply a sigmoid function on this. In this case, we are applying a sigmoid function on it, and this will be the output of this node. And the same thing happens with every node. And then when we go to next layer, it again takes the output from previous layer and makes a linear combination of those. So again, the linear combination here will be its weights. So W1 times the output of this node plus W2 times output of this node, W3 times and Wn times output of this node. That's the sum of all those products, and then they use a sigmoid function. Again, the same thing. So a deep neural network or a neural network is just a function of linear combination of previous layers, which is again a function of linear combination of previous layers, which is a function of linear combination of all the input points. And there are multiple linear combinations here depending on how many nodes you use, and then you have one final output in this case because it's a classification problem. So you have you use a sigmoid function. Yeah, so if you have a multi-class classification, you can use sigmoid function, but that will be more complicated if you use a sigmoid function to classify for each class. So sorry, if you use a separate network with one sigmoid output, sigmoid function output for each class, you'll have to train multiple networks. But there are functions, there is a function called softmax. Many of you have heard about it. It can predict multiple classes in just one, using just one neural network. So now that we know the basics of neural networks and what constitutes a neural network, let's look at the process for training the network. We use training data to train the network, and the two processes involved are feed forward and back propagation. So what is feed forward? So basically, it's predicting based on the current values of weights. Um, you have your training data, you pass it through the network, and you output a prediction, and it's called y hat instead of y, the actual value of y. So here you are taking x1, x2 as input, and you're running those through this network, and you predict y hat. And in this equation, again, you can see the idea behind a neural network. You have this input x1, x2, and then you multiply with this matrix of weights. So this will be a dot product. So this will give you w1 1 x1 plus w2 1 x2 plus w3 1 x1. Same for the second set of weights. This will be first node, second node. You take sigmoid of those, then again it's the sigmoid of the linear combination of what comes out from here, and that's your y hat. So in feed forward, you just take your training data, all the data points, and you predict y hat for all of them, so that you can later you can compare the value of y hat with your actual value of y, whether it is 1 or 0 for a binary classification problem. Yes, so this is the feed forward for a multi-layer network. Again, we start from right in this equation, right to left. So x is set of these points. We take dot product, then take sigmoid of that, and so on and so on. So this also represents the basic functioning of a neural network. Right. So let's talk about the error function now. As you can see, what error function means, what is the error? So what is the difference between our prediction of y, which we call y hat, and the actual value of y? We already have the actual values of y because it's a training data, and so we are using this to train our weights. So once you have passed the data points through the network and you predict y hats, what do you do next? You compare y hat with the actual values of y, and you compute this error function. Now let's take a more detailed look, more deep look into this error function. How does this work? And so this error function is for binary classification only. So let's see how it works. You have your value of actual y as 0 or 1. That's here, here, and you have your y hat predicted, it has value between 0 and 1. It could be very close to 0, between 0 and 1, and close to 1, either way. So how does this error function compute the error, and why do we use this error function? So let's suppose say that your actual value of y is 0. Okay, so let's just consider this for one data points instead of m examples or m data points. So if your y is 0, your first term becomes 0, and your second term is just negative log of 1 minus y hat. Now, if the predicted y hat that you predicted is 0.7, so it's going away from 0. So it's your weights are predicting exactly opposite. That means you have you need to reduce this error. You have a higher error. On the other hand, if you have your y hat as 0.1, it's closer to 0. So your weights are going in good direction. They're doing a good job. So you have a lower error. So what this function gives out is that if your y hat has a value closer to your actual value, it will already have a low error. So the minimization function won't work as hard as when it will work when you have a higher error. So, and the same thing goes for y equals 1. So when we I'll come back to y equal to 0 again. So when you compare these two errors, this is more negative, so it's a low value, and this is higher negative. So your minimization function has an incentive to even reduce this to a lower value, and by reducing this to lower value, it will adjust the weights such that this y hat becomes low and it goes closer to 0. Same thing happens for y equals 1, but in the reverse direction. If y is 1, this term becomes 0, and this term is just minus log of y hat. And you can use the same logic again, and then you'll realize that you will understand how the function is working. And this was just for one data point. Your error function will be your average over all the errors of all the data points. So you do 1 over m times the sum of all the errors, all the individual errors. And our objective in the end is to minimize the error function. So once you have computed your error, what do you do with it next? How do you use it? That's when backpropagation comes into effect. So you computed your error function, then you need to adjust your weights. So for that, you need to first compute the gradient of the error function. Once you compute the gradient of the error function, you can update your weights using the gradients. So the gradient is just derivative of the error with respect to each individual weights, as you can see here, including the bias. So how do you proceed with this? So once you have computed all the derivatives of error function with respect to each weight, as you can see here, you can use each of those gradients. These are called gradients. Each of those gradients to update your individual weights. So now say, for example, this is your error function and this is some weight, say W11. Now, if increasing my weight is increasing the error function, that means I need to reduce my weight because I want to reduce the error, right? So if increasing this increases the error function, this ratio is going to be a positive number, and this equation will end up reducing your original your previous value of the weight. And in the other way, if increasing the weight is reducing the error function, that means you should increase the weight even more to reduce the error function even more. So if increasing the error function reduces your increasing the weights reduces your error. So this this ratio is going to be negative. So this overall is going to be positive, and this equation will end up increasing the value of your weight. So this is how that uh, update function for your weights work. This alpha is a learning rate parameter. It decides how fast you want to update your weights. So how it decides the magnitude of the increments or the decrease in the previous value of the weight. And this is a hyperparameter which will be trained. So this is a parameter you have to you will have to feed it to the function. So let's move on. Yeah. So this is an example of how you compute your gradients. So in this example, let's start from H. So H is a linear combination of sigmoid of H1 plus sigmoid of H2 and W31. So these weights and these weights are used to compute a linear combination of the outputs from these two nodes and the bias. And these two nodes individually are also linear combinations of the previous layer or the input layer in this case. So H2 is it has its own weight matrix, vector times the inputs, and H1 has the its own weight vector and times the inputs. And in the end, you take a sigmoid of H to predict y hat, right? So how do you compute the derivative of error function with respect to this weight W11? So that's here. So you can use chain rule for that. So you first take, so I'll go back. So you can use chain rule for that, but you should know what are the functions, what is the link between these functions. So you can see here, y hat is sigmoid function, sigmoid of h, and h in turn is sigmoid of these two, and h is done sigmoid of h1, and h1 is a linear combination of x1, x2, x3. So in order to find the derivative of E with respect to this weight 1, 1, you first take derivative of E with respect to y, then y with respect to h, then h with respect to h1, and then h1 with respect to w11. So we didn't touch h2 here because in this link, in this pathway, we didn't have, in this graph, we didn't have h2. And by chain rule, you can just multiply this derivatives and you get this final gradient. And then you use this to update each of those weights similarly. So now now that you have completed one round of training, that's take your training data with X and your label Y, you feed forward it to your current network, and then you compute error function, then you compute your gradients and update your weights. And then you have one set of weights of your neural network. Now, how do you decide if this set of weights are good enough? You need to, obviously, you have to compute the error function, error, and you have to compute the accuracy, and you have to also test this trained network against an unseen data, which is the test data. Until now, you used training data, you had all the information about the actual Y, but now you need to test it against an unseen data for which you don't know uh, the value of Y. You can compare it later, but you don't know while training it. And if after training, so if after testing, you don't get enough accuracy with your testing set, that means you have overfitted your network. So if while training you get this kind of decision boundary between the 2 points, you you will have very low training error, very high training accuracy, but you need to make sure if this high training accuracy is good enough for even an unseen data, or is it a more generalized network that you have trained. You need to make sure that it's your network isn't overfitting your training data. So how do we test that is you obviously have a training error, you compute on training data, and you also test your trained network on a testing data. And you can see these 4 scenarios here. Epoch is a one round of training, feed forward and back propagation on all examples. That's one round. So if training error is big, obviously you don't want a neural network with high training error. So even if you test it on a testing error, it will have a high error. It might have a lower error than training error, but it's not good enough if it has high training error. Then there is a just right network. It has a low training error, but it also has low testing error. That means this network is a generalizing network. It's not overfitting the training data. And this was after one epoch. This was after um, running 20 rounds of training on your training data. So 20 epochs, 100 epochs, you will have very low training error, but your testing error might start increasing, because again here you are starting to overfit uh, your network on your training data, and same goes for even higher epochs. So this is just an example. It depends on your network and your task. Here on epoch 20, this network did a good job. On epoch 100, it had low training error, high test error, but it depends on your network. It might have different values for training error and testing error depending on number of epochs. So the point is that you have to avoid overfitting. And how do you know if you are overfitting or underfitting is by comparing your error against a testing data. So if you found out that your neural network is overfitting, so how do you fix that? So what's happening is that when you have large coefficients, that is the large weights, you overfit. Uh, you're overfitting your training data if you have large weight. So in the previous example, we saw that if increasing the weights decreases the error, this is positive, and you reduce. Uh, oh, this is negative, and you increase the weights even more. But you did that only on the training set. And for training set, it might have worked that increasing the weights is decreasing the error. But in reality, on testing data, it might not work. It might be that increasing the weights is actually increasing the error. So what we need to do is we need to penalize the large weights uh, in your network. So how do we do that? Is we modify the error function so that the incremental term is a function of your weights. So if you have higher weights, your error will increase, and same is the case for this. These are two ways of um, adding the regularization term, is L1 norm and L2 norm. But yeah, if you this if increasing the weights is increasing the error, so this sends the signal to uh, your minimization function that increasing weights is increasing error, so you need to reduce your weights. And this way the high weights that are causing overfitting can be reduced. So backpropagation works more to reduce the weights even more. So that's one way of reducing overfitting. Another way is dropout. So this is an example from the lesson, neural network lesson in the classroom, that if you are just using one arm to work out and you are not using the other arm, so this arm will become too strong and the other arm will stay tiny, and nobody wants to see that. So what happens and why do we need dropout? So if the weights of certain nodes are too high, they end up dominating the training process. The weights that have low, so the nodes that have low weights, they are not participating enough in training, so they don't get trained enough. That's why these nodes end up having higher and higher weights, and these will not get trained at all. So to avoid that, what you can do is randomly you can drop some of the nodes from training, so that other nodes get equal chance of training, and so this will balance out the weights. No one node will have such weights that are big enough that will lead to overfitting. So how do we do this? So during each epoch, you drop some of the weights, so with some probability. So let's say we use 0.2 as the probability in your dropout function. It will drop, suppose you have 100 nodes, so it will train only 80 nodes at a time, and it will drop 20 nodes from the training. And this is done randomly. It selects nodes to train. And so this way is better. Uh, this way is useful in reducing the overfitting of your network. That's one more way, and it's used very regularly. Dropout function. Another problem that you might have is of vanishing gradients. What what are these vanishing gradients? So now this is the graph of a sigmoid function, right? And as you increase x, the curve of this graph becomes flatter, and it becomes flat very fast right from here on both sides. So the gradient, the derivative of this are going to be very small because the slope is getting flatter and flatter. So what is the significance of this? Why do we care about this? So let's see. Now, as we saw previously, when we compute the gradients of weights at the very beginning of our neural networks, they depend on the gradients, not the gradient with respect to error, but the derivatives. They depend on all these derivatives. And if we are using a sigmoid function, all those derivatives are going to be between 0 and 1. And so the product of numbers between 0 and 1 and product of many numbers between 0 and 1 will end up making this gradient very small. So some of them even becomes very close to 0. So why is this bad? Why having small gradient a bad thing? Because because of this, if your gradient is very small, your weights don't get updated as fast enough. They will update very, very slowly, and some of them won't even update because these become very close to zero sometimes. So if your minimum is here, it will take a lot of time for your error function to reach here if your gradients are very, very small. So how do we avoid these derivatives with very small value? This is what we need to avoid. So how do we do that? We use another activation function. So to avoid this flat area, flat region, which gives us small derivatives, we need to use kind of activation function that give higher derivatives, or the ones that don't flatten that fast. They flatten slowly. Tanh is one of the functions. It gives out values between -1 to 1. Sigmoid gave out value between 0 and 1. But the useful part of tanh is that it flattens very slowly. So it gives higher derivatives as compared to sigmoid for a long time. It doesn't flatten out right away. Another important activation function is ReLU. It's the rectified linear unit. So the equation of this says that if my x is less than 0, I will call it 0. I will call it 0. If it's greater than 0, I will call it as it is. So here it's going to be at either x or 0, max of x or 0. So again, and so the derivative here is going to be 1. So again, you avoid the small derivatives in this case as well. And people who are practicing deep learning for some time, they know that we mostly use ReLU in the hidden layers, and we use other activation functions, tanh, softmax, or sigmoid for output layer. So yeah, so this is how an updated network will look like. You don't use sigmoid in the hidden layers, and you use sigmoid here if it's a binary classification. You will use softmax for multiple classification. In your nanodegree program, later in the nanodegree program, you have projects where you have to compute the q values from a current state and action. So in that case, the q value can be any number. It doesn't have to be between 0 or 1, or it doesn't have to be between -1 and 1. So in that case, even here, you use ReLU function for q values. For some projects, you have to predict action given a state, and for that environment, the action is between -1 to 1. So in that case, your output function will have tanh. Yeah, so these are the different functions that you can use. Mostly, I mean, almost many people use ReLU in the hidden layers, rectified linear unit. And there are many other variations of ReLU. You are most welcome to check them out online. So yeah, we are almost at the end. So this is how the updated network looks like. There is another improvement in neural networks is to use stochastic gradient descent. So instead of using the whole data set in one epoch, so you use the whole, suppose you have thousands of data points or even millions of data points, and you run all of them through the network once and then back propagate them all. It takes a lot of time, and until that training process is over, you don't know if you are going in the right direction or not, or if you need to make any changes to the network. So instead of that, we use the training data set in small batches. small batches, and we run those small batches through the network, perform the training one for each batch, one at a time, and then we keep an eye on the accuracy of the network. There are functions. If you are using PyTorch or Keras, all of them have the simple syntax for using batch. Using a stochastic gradient descent. There, and you can also early stop. So if you are using small batches, and if you see you have reached a good, you have gotten a good accuracy, or if you are going in wrong direction, you have the option of stopping in between, stopping the training in between. So using small batches is a better use of your resources and time, and it also leads to faster conversion because the network is updating stochastically, dynamically at the same time. So yeah, so this was a small presentation on the very basics of neural network. I'm sure I haven't covered many other things going on in the research community in the neural networks, but it does cover all the basic things, basic points you need to know, basics of neural networks. Again, I will repeat, its function of a linear combination of function of linear combination of the functions of linear combination of input data. Feed forward you use to predict a y hat. Backpropagation is used to compute gradients and update your weights. And then there are some good ways of preventing overfitting, like regularization. Then there is a dropout regularization that we discussed. Then there is a problem of vanishing gradients, and how to solve it is that we use ReLU functions in the hidden layers as activation. And we saw how stochastic gradient descent is better use of your resources, computing resources. So that's all from my side. If there are any questions, please let me know. Okay, so I'm going to end this webinar. This was all the basics of neural network. So thanks for watching. And I will also post the link, obviously, for the recorded webinar, and you can watch it later. And you can ask me later anytime on Slack. Thanks again. Bye.